Nature of work. So what do we understand by nature of work? The nature of work can be either positive, zero or negative, right? It entirely depends on the angle formed between direction of motion and applied force. Case number 1, if the angle between force and displacement vector is an acute angle, then the work done is termed as positive work done. Case number 2, when the angle between force and displacement is perpendicular to each other. In that case, work done is termed as 0. And case number 3, if the angle between force and displacement vector is obtuse angle, then in that particular case it is termed as negative work done, right? Now, since we have developed enough knowledge about work, let us talk about energy. So the energy of a body is signified by body's capacity to do work. Basically, it is a scalar quantity and shares the same unit as that of work. So energy is nothing but body's capacity to perform or to do the given work. In mechanics, both kinetic and potential energies are involved with dynamics of the body. So let us see what do we mean by potential energy. Potential energy of a body is energy which is possessed by virtue of its position or due to its state, right? It is independent of the way in which body is transformed in its state. Although it is a relative parameter, it depends upon its value in the reference level. We can define the change in potential energy as negative of work done by conservative force in the operation in carrying a body from one reference point to another reference point or to another point, right? So potential energy arises either due to position or condition of the given body. So here you can see ball which a person is holding, it is having a potential energy, and when a person throws that ball, it will convert into a kinetic energy. So now ball will have kinetic energy. So the potential energy which was stored inside a ball when a person was holding that ball will be transformed into kinetic energy when that person throws that ball. Talking about gravitational potential energy. So suppose if we lift a block through some height from A to B, then work done defying the gravity, right? The work done in such a case is stored normally in the form of gravitational potential energy. So therefore we can write gravitational potential energy as mass into gravity into that particular height, right? So whenever work done against the gravity, it is gravitational potential energy. The next comes is elastic potential energy. Suppose we are having a spring, right? And when that spring is either elongated or it is compressed, either we stretch it or we compress it, then work done against that spring, and that will be restoring inside that spring, and it is nothing but elastic potential energy. The resultant work done is stored in the spring in the form of elasticity, and that is termed as elastic potential energy. Next will be nature of restoring forces. So suppose if a string is extended or compressed to a distance x, right, the spring will then exert a restoring force equal and opposite to that particular change, which is x. that is a restoring, right? Whenever you are applying any force, equal and opposite force will be there to restore that force. And last is the spring. So in case of a spring, natural length of the spring is assumed to be reference point and corresponding always assigned to be zero potential energy. However, due to gravity, we can choose any point as our reference point, and hence it is having some potential energy values. Now let us talk about relationship between force and potential energy. So here you can see point A and B. The distance between point A and B is delta R. So let us assume a body is taken from point A to point B in such a way that there is no net change in its kinetic energy. Then work done is change in potential energy. So force into displacement F into delta R is given by U minus U plus delta U. So minus delta U is nothing but small change in energy due to change in position, right? The next term is kinetic energy. So kinetic energy is the energy possessed by virtue of motion of any object. Therefore, body of mass m and moving with a velocity v, right? If we are having a body whose mass is m and its velocity is v, we can give its kinetic energy by 1 by 2 mv square, half mv square, right? So kinetic energy is also a relative parameter over here. Now the next thing is equilibrium. So what do we mean by the word equilibrium? Law of motion we have already studied, right? That there is what do we mean by law of motion? That a body is said to be translatory equilibrium only if net forces acting on the body is zero. If all the forces which are acting on the body summation will be zero, then it is nothing but the body is in the equilibrium position. So F equals to minus du by dr, and when this minus du by dr, that is net change of force, is equal to zero, it is termed as equilibrium. So under equilibrium we are having three different conditions. If d square u by dr square is greater than 0, then it is stable equilibrium. If d square u by dr square is less than 0, then it is unstable equilibrium. And if d square u by dr square is equals to 0, then it is a neutral equilibrium, right? So these three conditions are very important to remember. Now let's talk about work energy theorem. Suppose that a particle is acted upon various forces and consequently undergoes a displacement. Then there is a change in its kinetic energy, right? So net work is equal to final kinetic energy minus initial kinetic energy, or you can simply write it as change in kinetic energy, right? So this is what work energy theorem predicts or states. Now let us talk about capacitors. So what do we mean by the word capacitor? A capacitor is a device used to store electrical energy or electrical charge, right? A capacitor is a device which is used to store either electrical energy or electrical charge. It consists of two electrical conductors which are separated by some predefined distance. The space between these capacitors may be simply a vacuum, and in that case it is known as vacuum capacitor. However, if the space is filled with any insulating material, it becomes a dielectric capacitor, right? So here you can see the capacitor. These are A and B, and the space between them is D. So the capacitance C of a capacitor is defined as ratio of maximum charge that can be stored in a capacitor to the applied voltage. Maximum charge which a capacitor can store to voltage applied across the plate is defined as capacitance, right? Now, conductors. In electrical engineering, a conductor is defined as an object or type of material that will allow the flow of charge in one or more directions. Material made of metals are common electrical conductors, right? So this is a conductor, a device which allows electrical charge to flow through it. So here you can see it. This is a conductor basically, right? The main properties of electrical conductors are: a conductor will always allow free movement of electrons or ions. Then the electric field inside a conductor must be zero to permit electron and ion to move through it easily. Then charge density inside conductor is zero, that is positive and negative charges cancels inside a conductor. As no charge is there inside the conductor, only free charge can exist only on the surface of a conductor, and electric field is perpendicular to the surface of conductor, right? Now, what do we mean by types of conductor? There are basically, we can classify conductors. So electrical conductors can be classified based on ohmic response. So there are ohmic conductors. Ohmic response or ohmic conductor means those conductors which follows Ohm's law. We all know that according to Ohm's law, V is directly proportional to I, or V equals to I into R, right? So if any conductor follows Ohm's law, then it is termed as ohmic conductor. And there is next category, which is non-ohmic conductor. All those conductors which do not follow ohmic law are termed as non-ohmic conductor. Example of non-ohmic conductor are LDR, that is light dependent resistor, diodes, thermistors, etc. Now let us talk about Laplace transform. So what do we mean by Laplace transform? Laplace transform is basically an application to transform the given f into another time domain, right? When we want to change the domain of given particular entity, we use Laplace transform. So f is a real or complex valued function of time variable t greater than 0, and s is real or complex parameter. So f of t must be a piecewise continuous function in the given domain. We represent Laplace as L equals to function, right? So it is given by integration of 0 to infinite e raised to minus st f of t, that is given function, into dt. When you will solve it, you will convert your given function into Laplace form. So this is step function. Step function means the value of given function is 1 for all the values of t greater than 0. In that case, when you put this value f of t equals to 1 in the given Laplace form, that is 0 to infinite e raised to minus st, and instead of writing f of t, you just write this 1 dt, and then just simply integrate 0 to infinite e raised to minus st dt. It will give you 1 by s after putting the limit of 0 at infinity. These are some important functions of Laplace and inverse of Laplace we must remember, right? Here are some Laplace transform. So now talking about last topic, which is electric displacement. So what do we mean by electric displacement? Electric displacement refers to displacement of electric charge across a conductor positioned in an electric field, right? So that is electric displacement. It fundamentally measures the charge per unit area, and you can also refer to as electric flux density. Therefore, it applies to free electric charge, thus eliminating the involvement of charge present in molecule or neutral atoms, right? So electric displacement is nothing but displacement of electric charge in the given condition. So how does electric displacement work? Electric displacement calculate density of electric flux as we have already discussed. It takes into account instant when you introduce dielectric into the apparatus, and a dielectric refers to an insulating material that lack any free or loosely bound atoms, right? Consequently, they fail to necessitate the movement of free atoms or free electrons along the surface area. However, if you introduce an insulated object between electric field, it will witnesses a degree of polarization, and it is because of that strongly bounded negative charge move slightly towards the positive conductor, which will help us to determine electric displacement, right? So this is how we can find electric displacement. So now talking about what is equation of electric displacement. So electric displacement is given by, as you can see here, D equals to epsilon 0 E plus P. Here epsilon 0 is vacuum permittivity and P is polarization density, and E is the electric displacement which we are referring, right? And SI unit of this is C per meter square, that is Colombo per meter square. Here C stands for Colombo, which is unit of electric charge.